All right. Good morning, everyone. Well, it doesn't have to be morning for you. It could be afternoon. It should be afternoon because you should be watching this in place of class 2D. So good afternoon. This morning for me, because of course I'm recording this in the morning. But I hope you all had a good day and all of that. So let's pray and begin. Dear Lord, thank you for bringing all my students here to class today. Continue to bless them, open up their minds, help them that they'll understand whatever I'm teaching today, and help them that they'll feel free to message me on WhatsApp if they don't understand anything. Keep them safe again. In Jesus' name we pray. Amen. Okay, cool. So let's begin. Ooh. So this kind of a hint of what we're going to go through today, neutralization reactions. But before we do that, let's go back a little bit, right? Because neutralization reactions deals with concentration closely. Last class, we learned a formula for concentration. By now, you would have had the compilation of most formula that I would have sent to you. So we know that, oh, that's my alarm. Sorry. We know that concentration equals moles over dm cubed. And we looked at this question here and we said, okay, if we have 0.3 moles and 350 cm cubed, how do you find the concentration? Well, first it's dm cubed. So we convert cm cubed to dm cubed, and that will give us 0.35 dm cubed. So you put 0.3 over 0.35, and we got something like 0.8, 0.85, yeah? And it's written like 0. Well, let me do the calculation. So it'll actually be 0.86. 0.86 moles per dm cube. That's how concentration is written, right? It's written as a mole per dm cube. And of course, you all know that was just a bit of memory jogging. So let's look at neutralization reactions. That's what we're going to look at today. So a neutralization reaction is just that. When an acid and a base combine to form something neutral. Looks like this. Yeah, so acid and a base, they combine to form salt and water. So when they combine, what the product is no longer acidic, it's no longer basic. It has a neutral pH. And if you'll remember the pH scale, we know that acids range from 0 to 6 and bases range from 8 to 14, but it's neither of those when it combines. It kind of evens out. The pHs, they kind of neutralize into 7. So it has a pH of neutral and it's the same pH as water, right? So neutralization reactions are when acids and bases combine to form salt and water, which is a neutral solution. All right, and we see some common examples here. Let's look more in depth into a definition as to what a neutralization reaction is. Well, a neutralization reaction is when an acid and a base react to form salt and water. A strong acid will react with a strong base to form a neutral pH 7 solution, and we just saw that there, right? And here are some examples of neutralization reactions. So we have some hydrochloric acid with some potassium hydroxide. It forms a salt and a water, the salt being potassium chloride and water. Okay, so this reaction here is already a neutral reaction because we have the acid and the base forming salt and water, which is neutral. And if you look at all the bases, you would see that all of them are hydroxides. Most bases are hydroxides, right? So you have potassium hydroxide, we have magnesium hydroxide, we have iron hydroxide and sodium hydroxide. And well, the acids are all HCl in this case for whatever reason. But we see that they form all a salt and water. salt, and water, salt and water. So these are the types of neutralization reactions that you would see. So in a CXC question, they won't really give you this. They would give you more of a worded statement, but this is basically what they're asking you. All right. So you can see it here. This is a common one. HCl plus NaOH gives you table salt, sodium chloride, and water. Moving on. So titrations or volumetric analysis is what we use when we're talking about neutralization reactions. But before we go there, let's look at some indicators, right? And it's very important to look at indicators when we're dealing with these type of reactions. Why? Because indicators are specific to pH. So if I use something like, and I can never pronounce this word, phenolphthalein, it's very common in your labs. If you were doing titration experiments, you would have definitely used this one. Or at least that's what I used when I was going to school. So it's a common indicator. In acid, it's clear, but in alkali, it's pink, just like this. So you can see that in acid, it was a little bit clear. And then as alkali started to add to it more and more, it became pinker and pinker. And methyl orange is the same thing in acid, it's red, but in alkali, it's yellow. And it changed from red to orange to yellow. And you can see the same thing for methyl red and bromothiol blue. All right, now why is this important? Well, we were talking about neutralization reactions, and we were talking about adding base to acid. So we need to know in a neutralization reaction when things are neutral. So what they do is they add a few drops of indicator, something like this, that would be a specific color in acid and a different color in base. And they add, let's say they add phenolphthalein to an acid, right? It's colorless. As you start adding base, what happens is that changes to pink. However, before it changes to pink, because acid and base forms a neutralization reaction, it actually goes a little light pink like this before it fully changes to this pink, this darker pink that you see here. And when it's this light pink here, right before it changes to the dark pink in alkali, you can see, well, that reaction has become neutral. And it's very important to know when that reaction has become neutral, because it means that the neutralization reaction has occurred. Yes? Now, if you're lost, stay with me. We're going to keep going. You'll understand just now if you're a little bit lost. So let's look at neutralization point then. Maybe this might help. So a neutralization point is determined through volumetric analysis. It happens when an acid or base reacts, and the point at which the acid or base is used up and has a pH of 7 is called the neutralization point. Now, neutralization point can be determined in 2 ways. Let's see how. So it can be determined through titration, as you always see this little GIF here, and it can be determined thermometrically. But let's deal with titration first. So what is a titration? A titration combines lab work with calculation. So several drops of indicator are placed in a known volume of acid, and the acid is run carefully from a burette until the exact point when the indicator changes color. This point is called neutralization. So you all could see here that the person is swirling and getting a faint pink color. And right before that pink color is totally taken over the solution, that is the neutralization point. So in a titration reaction, you actually have to look at the conical flask carefully in order to not overshoot the experiment. So let's read it again. Several drops of indicator are placed in a known volume of acid or base. The acid is run carefully from a burette until the exact point when the indicator changes color. So remember, the indicator was clear in the acid all the time. At a point where it changes color, at that exact point, that is when the neutralization of the acid and the base happens. And it's very important to know that. Let's go back a little bit. So what is the purpose of determining neutralization point? Why do we have to look at the exact time when the indicator changes color? Well, an acid-base titration is used to determine the unknown concentration of an acid or a base by neutralizing it with an acid or a base of known concentration. So it says, I have the known concentration of this acid, but I do not know how much this base is. I don't know what concentration this base is. So let me run some base into this acid and find a neutralization point, right? When I take the volume of the base that I have run into the acid, like this, so you're seeing some base dropping into the acid. When I take the volume of how much I've put into the acid, determining the neutralization point, I would be able to then calculate how many moles of base I have using the concentration formula. So let's go back a little bit. So if I have dm cube, that is the amount of volume that I was given through the burette. And of course, I've written out my chemical equation, so I know the moles, then I'll be able to calculate concentration. But I need to know the specific volume used. And that is the point of titrations. To run, let's go back. To run base into acid at a specific point until it turns this, until there's a change in color. And the burette measures the amount of base that it takes to do that. Now it can be in reverse. I could run anything that is unknown. I could try to put it up there and see, well, let's say it's acid in the top there and base at the bottom, and I want to find concentration. I can do that too, right? Using the chemical equation, of course. So let's go back. So we said that acid-base titration is used to determine the unknown concentration of an acid or base by neutralizing it with an acid or base of a known concentration. This technique, the unknown concentration, using this technique, the unknown concentration can be determined. It makes use of the neutralization reaction that occurs between acids and bases, and the knowledge of how acids and bases will react if their formulas are known. So observe the chemical formula below. Let's look at hydrochloric acid and magnesium hydroxide. They form 2 moles of water and 1 mole of magnesium chloride. Now, it's not really 2 moles, right? It's 2 molar ratio. So let's say there are 2 moles of magnesium hydroxide. That means there'll be 4 moles of hydrochloric acid. There'll also be 4 moles of water and 2 moles of magnesium chloride, right? This is just that we're supposing. In a question where concentration of hydrochloric acid is given, so we know the concentration of hydrochloric acid, right? Then by using mole ratio, we can determine the concentration of magnesium hydroxide needed for the reaction to occur. Can we do that? So the concentration of hydrochloric acid is given. The moles are also given. So what you do is you divide the moles by the concentration to see the volume. Yeah? And you can do the same thing for magnesium hydroxide, given that you have a volume. So in a titration, you're running this magnesium hydroxide into this hydrochloric acid. And you look carefully in the clinical flask to see the point at which the indicator changes color. Now, the burette that you're running the base from, it is measured, so you can see exactly how much base you're adding. When you've added enough base and the solution has changed color, you take that volume from the burette reading, then you calculate using the moles, you multiply DMQ by moles, and you find the concentration. That's basically what volumetric analysis or titration does. So that's the titration. Now it can also be determined thermometrically. So you'd be doing the same thing. You'd be running some base and some acid, but instead of having an indicator, you would have a thermometer. And the highest point at the solution, the highest point where the solution, what am I saying? The highest point that the solution reaches, sorry, is when the solution has been neutralized. So that's called the neutralization point. So you can see here that the solution reached a high point of, let's call this 33.5. Yeah, that's the highest point that it reached. So the volume used was 80. Now you can overshoot, you could add 100, you could add 120, but that just means that you'll be missing the neutralization point. So here in the titration, I could add way more than I actually need, but it's I need to be very careful that I don't, in order to find the correct volume needed, in order to find the correct concentration of the unknown basic solution. All right, let's look at a titration example here, right? So we have the burette. Remember, we said it was marked, right? So you would know exactly how much base you're adding into the unknown concentration. So let's say it took a total volume of 800 cm cube of magnesium hydroxide solution of a concentration of 0.3 mole cm cube to neutralize 250 cm cube of magnesium hydroxide. This is supposed to be of HCl. Let me correct that now. Sorry about that. Yes, so let's do that again. It took a total of 800 cm cube of magnesium hydroxide solution of concentration 0.3 dm cube to neutralize 250 cm cube of HCl. So while we're doing our titrations and we ran the base into the acid, at the point of neutralization, we saw through the readings here that it took 800 cm cube, yeah, to neutralize the acid. And we saw that using the indicator. 24 moles of magnesium hydroxide were used. Therefore, 0.48 moles of hydrochloric acid were used, because we could see that the ratio is 1 to 2. So if 0.24 moles of magnesium hydroxide was used, then 0.48 moles of hydrochloric acid was used. The concentration of HCl was determined to be 1.92 moles per dm cube, or some people would say 2 moles per dm cube. So let's see how we got that. Well, we took the volume of magnesium hydroxide used, and it was 800 cm cube. So we convert that to dm cube and we put it right here. Then we use the concentration. The concentration of the base was 0.3. Yeah. So when we multiplied it, we got the moles. The moles was 0.24. We were able to then plug this into HCl. Using molar ratio, we multiply 0.24 by 2. 0.24 by 2, gives you 0.48. There was also 250 cm cube of HCl in the conical flask. So we put that here. When we divide 0.48 by 0.25, we have 1.92 concentration moles per dm cube. So that's how we were able to find what's happened when. Let's look at another example. So it says it takes 83 cm cube of 0.04 moles per dm cube of sodium hydroxide solution to neutralize 235 cm cube of hydrochloric acid solution. So by titration, they determined that, well, it took 83 cm cube of 0.045 moles per dm cube of sodium hydroxide to neutralize this acid of an unknown concentration. So what is the concentration of hydrochloric acid? Well, let's see. Concentration equals moles over dm cube. So let's look at our first triangle here. First triangle is NaOH. Let's plug in what we know for NaOH. Well, we know that there are 83 cm cube, which is 0.83 dm cube, and we know the concentration is 0.045 concentration. Yeah, so when we multiply that, we get 0.04 moles. So seeing that this is a 1-to-1 ratio, how many moles of hydrochloric acid is there? Let's see. Hydrochloric acid, there's of course 0.04 moles. And what else do we know about hydrochloric acid? Well, the question said it neutralized 235 cm cube. So that's 0.235 dm cube. What is the concentration? Well, the concentration was 0.17 moles per dm cube of hydrochloric acid. Simple, I think. So in volumetric analysis, they won't write it out for you. They would expect you to write it out for yourself and determine the molar ratio and then do the calculations, right? But that's what I want you all to do for me today. So the first question, I want you all to do these 3 questions. The first question says 25 cm cube of potassium hydroxide solution of concentration 0.6 moles per dm cube neutralizes 20 cm cube of an acid containing 0.5 moles per dm cube. Now, if we go back here, given this information, I don't only have to find concentration. I could find moles, I could find dm cube, I can find anything here in the triangle if I manipulate it correctly, right? This question, however, is asking you to find the moles. So what it does is it gives you dm cube, it gives you concentration. It's saying find the moles of the base, find the moles of the acid. When you do find those 2 things, determine the molar ratio. So you find the moles, let's say the moles is 2 of potassium hydroxide, and of acid it's 4. What is the molar ratio? Well, it's a 2-to-1 molar ratio, or 1-to-2, because it's 2 and 4, so 1-to-2. Yeah? And so the first question is asking you. Second question says, 25 cm cube of a solution of sodium carbonate required 22 cm cube of 0.04 mole per dm cube hydrochloric acid to completely neutralize. Calculate the concentration of sodium carbonate solution in moles per dm cube and grams per dm cube. So this is a straightforward titration question. It gives you everything you need to know. Except here, you need to convert moles to grams, and we know how to do that, right? Using the list of molar formula that I gave you. You can convert moles per dm cube to grams per dm cube. Do you have to write out a formula for this? 25 cm cube of solution of sodium carbonate required 22. Okay, yes, you do have to write out a formula for this. I'll put the formula in the group for you. And then there's a CXC question here. So it says determine the mass. Ooh, so mass. So we know that we need to find moles first and then determine the mass. So it says determine the mass of sodium thiosulfate required to make 250 cm cube of 0.80 molar. Now we know that molar is the same as moles per dm cube, right? Let's go back here. Right, we know that 6 big M is the same thing as 6 moles per dm cube. It's just a different way of writing things. Sometimes you might see this in CXC, but do not be confused, it's the same thing. Ooh. Right, 6 molar or 6 moles, sorry, 0.8 molar or moles per dm cube of sodium thiosulfate solution. The molar mass is 158 grams. So I'm not going to help you with this. All right, you all could cahoodle and get together on your own or together and do this. And I want this done for next class. I don't want it attempted, I want it done. Okay. Determine the mass of sodium thiosulfate required to make 250 cm cube of 0.08 moles per dm cube of sodium thiosulfate solution. Simple. What you do is you first convert this over to dm cube, and this is concentration. So you multiply it and you find the moles needed. And when you find the moles needed, you divide it by the molar mass to find the mass. And that's simple. Describe how you would make 250 cm cube solution of 0.08 moles per dm cube. So I changed it down here for you, right? So you won't get mixed up. So you would simply get this answer. So when you get the answer in grams, you would say, well, I would take 250 cm cube of water and dissolve whatever the grams is into the water, stir, and a solution will be formed. All right, when sodium thiosulfate reacts with hydrochloric acid, sodium chloride, water, sulfur, and sulfur dioxide are formed. Write a balanced chemical equation, including state symbols. So everybody but Jedi and Jen has to do this. You will be doing balanced chemical equations on Friday with me. So everybody else, Russell, Leon, Elon, you already balanced chemical equation, including state symbols. Considering that 5 cm cube of, and this is the big M again, right? Considering that 5 cm cube of 1 mole per dm cube hydrochloric acid was used, calculate the maximum mass of sulfur that can be formed during this reaction. So Jonathan, should I don't do this? We'll be doing this next class. So what you will have to do is write out the chemical equation, find the moles, look at the sulfur, find the molar ratio, then determine the mass. All right. Well, that's it for today, folks. I want you all to also do for me January 2021 question 1. Have that done for me for class. Yeah, and next class we'll go over these questions and some multiple choice. Actually, have this multiple choice done for me too. So multiple choice paper 2010, question 6, 7, and 8. This is not a review of what we just did. What's a review of, these questions is a review of what we just did. This would be a review of all the most questions. So you'll have to go back into the PowerPoint and review, refresh your brain, jog your memory, and you can answer this question, question 1, and 2010, 6, 7, and 8. All right, gang. It was a fun old time. I wish you all success in these questions. And if you all have any questions for me, please feel free to reach out. Thank you very much.